So this is kind of a meeting that had come out of the Polar Technology Conference that was last year. We were able to hold it by the skin of our teeth, but Mike Rose had been selected as a keynote speaker for that conference and was unable to travel due to COVID. So he has graciously accepted our request to give what would have been his presentation to the group and then to NSF as well, who I know there's definitely some interested parties here. And so Mike, would you like to introduce yourself?
Yes, so hello everyone. I'm Mike Rose. I'm Head of Engineering Technology at British Antarctic Survey. I've been here for a long time. I think I first joined BAS in 1988 to winter in the Antarctic, and there's always been some interesting project which has kept me here. So I've sort of been here a long time and spent a lot of time in the Antarctic, not very much in the Arctic. I'm an electronic engineer by trade, so that's me.
Great, thanks so much. Yeah, I think there's definitely been a lot of interest, especially in light of COVID, as just international travel has made getting to a lot of our normal logistics hubs more and more challenging. So actually, Mike, I'll go ahead and pass it off to you if you want to start your presentation and share your screen.
Yep, we'll go ahead.
Oh, and then as one last comment, we're going to be recording this. And so for those of you who couldn't make it, we'll definitely be circulating the link for that as well.
And so if hopefully you're seeing that.
We do, thanks.
Good. Yeah, so this is sort of a little bit of a refresh of the talk I was going to give in Boulder, but I've sort of updated it very slightly. So I think most people know where Halley Station is. It sits on the coast in East Antarctica. It's actually built on a floating ice shelf. So that's freshwater ice that's formed on the land and has flowed onto the sea. And it's about 200 meters thick. And it constantly accumulates. I'll talk a little bit more about that in a minute or two. And it's constantly flowing. And the current station is our sixth iteration of a station at Halley. We first built one there in 1953, and they've all either slowly crushed and buried under the ice, or they've become untenable because of their position close to the calving zone on the coast. So this is what the Brunt ice shelf looks like from the air. The whole thing has got about the same aspect ratio as a playing card. So although it feels fairly solid when you're standing on it or driving a big vehicle, the whole thing is actually quite a temporary feature, I guess. And it's in some sort of mass balance in that snow accumulates on the top of it, mostly blown there from somewhere else from the continent, and it flows and crumbles away at the edges in small icebergs, and it also melts off the bottom. But it's actually been growing ever since BAS has been there. The ice shelf has been getting bigger over time. So although it's in some sort of mass balance, it is actually growing, you see what I mean? And accumulation really is the major engineering practicality of being at Halley. So these two sets of photos are taken just a year apart, and it shows you the problems of being at Halley, and that it has been the defining problem to overcome in having a station there, which I'm not going to talk about the engineering behind the station generally, but it does mean that anything that we put down on the surface at Halley, we've either got to expect it to bury at the rate of about 1.5 meters a year, or we've got to try and raise it up out of the snow again 1.5 meters a year. And that is a major practical limitation on what we can do at Halley. So the ice shelf at Halley had got some glaciological features in it that we've sort of know about and we've been monitoring for a long time. And when we went from building Halley 6, which is here, or was there, from our old station at Halley 5, it was because we thought there was a danger that Halley 5 could peel off in a big iceberg. And at the time, this feature here, Chasm 1, had been totally dormant, really since satellite photographs of it began. So, you know, it'd been dormant since at least the 1970s, 80s. And after we built our new station in what we thought was a safe site here, suddenly in 2013, Chasm 1 started to become active and started to lengthen. And, you know, fairly obvious that this crack was headed for the grounding zone here, which holds the whole ice shelf in, and that our station was going to be on the wrong side of that crack. So we moved the whole station 23 kilometers to a new site, which we hope and think is glaciologically safe. And you know, that was fairly major project to move the whole station. But the new station design was specifically allowed that to happen. So we moved the whole station to its new site. But unfortunately, more or less during that season, in fact, just before that season started, at the very end of October 2016, just as we were about to embark on moving the station, another crack started here. And we called that crack because we spotted it in right at the end of October. We called it Halloween crack. And that very rapidly grew in length over that season. So we moved the station whilst that crack was growing, and we were keeping an eye on it. Because now we had sort of two active cracks that were moving quickly and complications of the way that they might interact with each other, we decided that it wasn't safe to winter staff at the station. So that was a fairly big deal for us, you know, and it was a big deal for the UK government. It had, you know, we'd had constant continual occupation since 1950, and we'd only had this new station which cost us a lot of money for a few years, and we pulled out of it. So you know, that was quite a big deal for us. And oh, I just thought I'd show you this. This is actually a satellite photograph which hasn't been highlighted to show things, so it's a bit easier to see. That's first chasm growing towards the rice rumples, and then this is the Halloween crack, and that's the grounding zone and where our station now is. So with a no, oh, actually, I just remembered why I put this slide in. So one of the things, one of the problems we saw once we stopped wintering people was that we also lost probably the ability to actually put large amounts of cargo ashore at Halley. So normally we do a sea ice relief into one of these creeks and then drag it to the station. We've got another creek to the north as well, but that one has also been cut off. So that normally it takes about 500 tons of stuff to run Halley each year, and we've lost the ability really to get, you know, big bits of cargo in or out. So with the not wintering, our science director and our director above him really asked the question is, well, how can we carry on with some science productivity from Halley? How can we maintain the data sets that have been running since the 1950s, and how can we carry on with some of the campaign science that we'd planned? And in particular, there was that problem of how do we do it if we probably can only get in or out by air. We actually thought we had one bite of the cherry of getting cargo in, and we were right. In the 2017-18 season, we managed to get the ship in and get cargo off it, but that was our last bite of the cherry. So when we looked at the sort of requirement of our director about saying, well, you know, I need science coming out of Halley, we looked at it and we realized actually that quite a lot of the science that runs at Halley was already reasonably automated, and we could run it as long as we could provide it with reasonable amounts of mains power. And we could provide resilience on some of our long-term data sets because we had field instruments which we could run as backups, things like automatic weather stations. We had some standalone magnetometers and things like that. And of course, we had all the infrastructure there already. You know, we had, and in particular, we had power distribution and IT infrastructure, although that did, and we thought it would need some modification. And without people there, you know, the science kit doesn't actually use that much power. So Halley normally used to run at about 200 kilowatts with people, but most of that was keeping the spacers and the people warm and happy, and providing, you know, moving water around for showers and all those sort of things. The actual science kit didn't take that much power, but we really did have a big logistic constraint. Was, you know, we had to, within a year, in fact less than a year, within about 9 months, any heavy stuff that we needed to get to the ice shelf to allow us to automate had to go in. So and we had to allow for the possibility that we might not even get that one ship call, and so anything we did, we had to at least have the possibility of it probably going in the back of an aircraft of some sort. And the two aircraft that we can land at Halley are either a Twin Otter or a Basler, so it's very limited on cargo capacity. And what we did, and are still doing, in fact, is that we provided some mains power, which is where the bulk of this talk is about to go to. And then we've prioritized experiments based upon really how easy it was to get them to run automatically, and some sort of metric on based on their science value. So if it was very easy, then we automated it, and if it was very valuable, we automated it. And we're now coming to some of the ones which are sort of harder to do and maybe not quite as scientifically productive. And as I say, it really all hinged on the providing mains power, provision of you know, sort of 10 kilowatts of normal voltage electricity, which for us in the UK is 230 volts. And we looked at several things. I'm not going to read them, and we basically came fairly rapidly to the conclusion that a microjet turbine was the way forward. It had the big benefit that it run on fuel that we already had on the station, and we had quite a lot of fuel on the station because we kept 2 years of wintering fuel available on the station. So we had quite a lot of fuel available already, and we thought it was going to be reasonably easy to do any necessary modifications to make it run in the Antarctic. And we could also, although we didn't have to, we could see that we could get it in bit form and actually sort of do the construction in Antarctica if we had to, although in the end we didn't need to. The disadvantage with it was there's really limited options. One company called Capstone have pretty much got the market sewn up, so you know, from this moment onwards, we are sort of a little bit vulnerable to Capstone, either withdrawing support for this particular model that we're using, or if they stop making it for, you know, if they went bust or anything like that, we would be it would be a bit of a dead end for us. I think it's worth just mentioning wind and solar combinations, because that would, you know, for a lot of people, they think that was the obvious way to go. And you know, Princess Elizabeth Station, run by the Belgians, is a good example of a station which actually produces a similar amount of power with wind and solar. Although it does have some diesel generators. I don't know how much they're used, but it does have diesel generators as backup. But the key difference for Princess Elizabeth is that they do have access to bare rock, and it comes back to the accumulation problem at Halley, is that if we put up wind generators and large amounts of solar panels, we have to keep lifting them each year, we have to maintain them. And actually, even running wind generators where you haven't got a solid foundation, you've got an ice foundation which flows, is actually very difficult. And Halley actually isn't as good a wind regime as Princess Elizabeth, although it is slightly better for solar. And rather surprisingly, when we looked, and in particular because Halley has some long periods of no wind, it tends to be in a bit more of a storm and calm regime, it would need very significant amounts of battery backup, and that would be very expensive if we had to get that in by air. So when we looked at it, we actually went, well, you know, the micro turbine was the only thing that we thought we could implement in the time frame that we had available to us. And rather surprisingly, it wasn't that much heavier on carbon than having wind and solar, because although we are burning diesel, we're burning after, the wind and solar would need a lot of vehicle movements to maintain it above the surface each year. So although wind and solar is lower carbon, it isn't actually that much lower on the carbon. So this is what the Capstone microturbine looks like. It's a bit like a jet engine in an aircraft, although it has only got one moving part. It's got one moving shaft with a turbine and a generator on it. That moving shaft is on air bearings, so there's no lubricant in there, there's no oil, there's no coolant in there, there's no liquid of any type, and because of that, it has very, very long service intervals, and in fact, even its 8,000 hour service interval, which is, you know, essentially a year, close to a year, even really its 8,000 hour service is a very minor service. So you spin it up, and once it's going, it basically keeps going. We implemented it in a container. We built the container in the UK and shipped it down with the things in. Oh, actually, should just say, in that last photograph, just the size. This is the 30 kilowatt model. You can just see that that's someone just disappearing behind it. So it's about the size of a large fridge, I guess. So we built it and put it into a 20-foot shipping container. We built it in the UK, although we did it in such a way that if we had to, we could have shipped down the parts and put them into a shipping container in Antarctica, and all the parts could have fitted into a Basler, or we had them already on site, like we had spare shipping containers on site and things. And one of the key things about the way that it's implemented is that the fuel tank is in the container with the microturbine. So this is a day tank which periodically refills, and the reason for that is that there is a constraint on the difference between the temperature of the air going into the turbine and the temperature of the fuel going into the turbine. They have to be within a few degrees centigrade of each other, and so by having the day tank fuel in with the turbine, that's achieved. Also in this photograph, it's worth pointing out, this is the exhaust of the microturbine, and it goes out here, and the air that's being used by the microturbine is coming in through a pipe within a pipe heat exchanger. So the air coming in is being warmed by the exhaust going out. And in fact, the thermal management of the microturbine has proved to be more difficult than we imagined and more critical than we imagined. So we have spent quite a bit of time getting that right now. We still have this pipe within a pipe heat exchanger, although it's a little bit shorter because we were running a little bit too warm. And we also have some active cooling, which blows air from outside into the container on warm days. And that is quite simple in its construction, and but the combination of two possibilities of air getting into the container, either via the heat exchanger or via these fans, makes its behavior actually quite complicated. But we have, so I think if we were starting again, we would probably think a bit more deeply about the thermal management, but we have ended up at a place where we can keep it reasonably good temperature. So we can keep it basically between 0 degrees C and about 18 degrees centigrade. It normally stays within those limits, despite the outside temperature going anywhere between -55 and 0, and with some extra cooling when we get gales. So the thermal management, we got sussed eventually, but it did take a little bit of more effort than we expected. So what we recognized at the start, which wasn't thermal management, but we recognized at the start that we would, whatever we did, we needed to make it reliable. It had to, it wasn't, if we couldn't make it run through the 9 months of the winter, which is about how long the Halley winter is, then it really wasn't worth doing, because the data sets we have at Halley are, have their best value in the fact that they're continuous. And we also wanted to make it environmentally very safe. We wanted to make it very unlikely that we could have a fuel leak. So we expected at our current power usage of about 10 kilowatts, a bit less, that we'd use about 40 tons of fuel a year, and that we'd have and that we would be having to move that 40 tons of fuel from outside bulk containers and into the day tank. And we really wanted to make sure that we didn't lose 40 tons of fuel into the snow, and we weren't going to have an environmental disaster. And the sort of philosophy that we took there was that if anything that we could think of that could possibly go wrong wouldn't make a fuel leak. There'd be something else that would protect us. And if any of those layers of protection failed, that we would know that they'd failed because we were monitoring them in some way, either with data system automatic measurements or with cameras. And we wanted the thing to be automatic, but we could intervene if we needed to. But it would basically look after itself without us having to do anything from the UK end. And as I say, that we were driven by this fact that we only really had one bite of the cherry of getting anything heavy in, and there was always the possibility that we might not even get that. So this is a good example of what we saw, the things that we did to make sure that it was environmentally safe, and the idea of having two things that would have to go wrong. So on the day tank, these are the level switches here, which if the fuel level reaches down to either of these two switches, which are nominally at the same level, then that initiates the pumps that pump the fuel from the external bulk tanks into the system. When the fuel gets to this float switch in the day tank, then that turns off the pumps. But if for any reason that switch stuck on, there's a higher level fuel switch which also cuts off the pumps. And in fact, in this system, in the fuel tank, because we thought this was a particularly possible, one of the weaker areas or one of the areas which had more possibility of leaking, we actually have another switch, which is a totally different mechanism higher up in the system. And we monitor fuel levels in those tanks, and I'll show you some monitoring in a little while. These are the outside bulk tanks. So these are 25-ton bulk tanks with AVTA in, and they're bunded, so the fuel can't spill from the tank in any way. We monitor them by webcam. We get a picture every 5 minutes. The hoses that come from them are on anti-siphon valves. So if the support system for the hose failed and the hose dropped to the ground, it won't leak. And the hoses are on dry brake connectors. So if there's anything, if there was a major storm and the hose managed to pull off, it shuts off. And the hoses themselves are actually in field-proof sleeves as well. So the hoses, if there was a leak in the hose, that would go into the fill sleeve, and the fill sleeve swells up, and we would spot that by the webcam. So as I say, we got several webcams around looking at different views and different things. Again, this one looks at the fuel lines, and these run night and day in good and bad weather, giving us an image every 5 minutes, which comes back to Cambridge. The data that comes back to Cambridge all comes back via our geostationary satellite system, but we also have most of it also comes back on a Iridium open port system as well, so that if we have if either of the satellite systems goes down for any reason, then we still get the data and we still have control of the system. This is probably the most boring web picture in the world, in that this picture updates every 5 minutes of the pumps, but you don't get to, obviously you don't actually see any change from 5 minutes to the next. But inside the container there is a bund as well, so if there was any fuel leak into the container, we would see it in this picture. And there is also a bund cut-off switch, so if the bund gets to just below half full, that would also cut off cut off the system dead, so that no more fuel could get pumped. A little peculiarity of the microturbine is that it doesn't actually like low loads, so that we built a circuit that makes sure that we keep it running above its minimum load. I can talk more about that if anyone's interested in that. And we get a lot of data back. So we get, I can't remember what the exact numbers of data streams we get back, but we get quite a lot of temperature data. We get pressures either side of the pumps, the fuel pumps. We got quite a lot of webcams. We get lots of Modbus information from the turbine and from our load bank, which is also Modbus. We got vibration monitors. We have lots of data, and I can show you some of that data in a little while. And of course, we also get science data back from the science experiments which are running as well. So this is a little bit of an example of the data. We use a program called Grafana to look at it, just time series of the various bits of data. So again, I can actually show you some of that live if at the end, if it's of any interest. And because fuel safety is really key for us, we do look at the fuel amounts in quite some detail. And there's quite a lot of complication in here. So one of the things, and that complication comes from the fact that fuel, diesel, and the aviation fuel that we use after, it has got a very large temperature coefficient, so it expands with an increase in temperature by quite a large amount. So if you're monitoring its levels, you have to try and adjust for that temperature compensation. We could measure the mass of the temperature of the fuel that we have, but that's actually quite difficult to do outside because the bulk tanks change with the amount of snow that is on top of them by quite a large amount as well. So it is actually quite a difficult thing to do to make sure that you know that you're not spilling fuel. So the way that we do that is that we both tried to say, well, we started in this particular year, we started off with 43,000 litres of fuel, and we tried to work out how much fuel we had left in the bulk tanks and how much fuel we'd burnt in the turbine, and that should have added up to that 43,000. And in fact, it added up to more than 43,000 because our temperature coefficient isn't perfect, but it sort of gave us some, gives us some degree of confidence that we're not spilling large amounts of fuel. And the other way we do it is we look at the amount of fuel that we take out of each bulk tank and the amount of fuel that we put into the day tank each time one of the refueling episodes happen. And they sort of happen about every 36 hours, depending on how much power we're using. So this just shows you the levels in the bulk tanks dropping and the level in the day tank going up. And we look at the difference in those. That has the same problem in that the temperature of the fuel changes as it comes into the container and things like that. But it also gives us another way of making sure that we're not just pouring fuel into the snow each time that we do a refueling. So although we spend, you know, the efforts that we do, we spend an awful lot of time on the microturbine and automating that. We've also done bits and pieces on the science experiment. So this is the called the Dobson. It's measures ozone. Halley sort of famous for detecting the ozone hole. Well, I have to say we were a bit lucky to do so, but and this is a very oldie world machine. It's normally run by people, you know, turning knobs and pushing levers and pressing buttons. And we've replaced that all with servos and computer control. So that all runs automatically. And then we've got a whole load of space weather experiments, which really were more or less automatic to start with. And we've just had to put some extra stuff around them so that if, say, for instance, a PC freezes, that we've got a way of rebooting the PC automatically. So, this is a list of everything we've done so far in terms of the science experiments that we're running at Halley. So we've done both some space weather ones, we've done the Dobson, we've done some atmospheric chemistry ones, and we have, of course, we have the normal meteorology suite. And Halley also now is producing quite a lot of data for the glaciology. Initially we had a network of GPSs and crack width measuring instruments to tell us about the risk of that the station could be under. But those themselves are actually now, as well as telling us about any risk that the station may have and the way that the cracks are developing, they're actually being quite a good scientific data set amongst themselves. So that is just a sunset shot of what we call the automation platform. So that is the one that has got the microturbine on it and the bulk fuel tanks next to it. And this was the slide for 2019. So this is like 1 year's worth of data. It would be similar for 2020. It ran in 2019 for 280 days of unattended operation. It went through 17 what I'd sort of call bad weather events, that sort of gale force wind, reasonably windy, maximum gust 73 knots, ambient down to minus 56, and we in that year burnt about 40,000 litres of AVTA. We're running about 9 kilowatts of power, and during that 280 days we had 145 automated fuel transfers from the bulk tanks, and there'll be similar numbers for this year, but I just haven't produced the stats for 2020 yet. And the plan on where we're going is on this current season just gone, is that we've sort of focused on some of the weak points that we know about in the system. We've added a few more automated experiments. We're adding in more fuel tank monitoring. We've added in an extra bulk tank into the system with another pump, so that we have also got redundancy in the bulk tanks. So if one potential reliability concern is the anti-siphon valves, it's pretty easy for them to fail shut. So if one of them did happen last year, it would have caused us to run out of fuel. But now we've got essentially a spare bulk tank, and we're carrying on next season, adding more atmospheric chemistry and some optical experiments, and we're working out our duty and standby arrangement. So we have 2 more microturbines here in the UK, and the intention is that we've already started, but the intention is we'll sort of perfect the arrangement by which, if one turbine was to stop, the second one would automatically take over, and then we'll ship one of those turbines to the Antarctic next time we get a shipping opportunity, and we'll keep one microturbine in the UK, which we'll use to train staff on and try out any changes or upgrades that we think. And we anticipate that we may get a ship call in the 22-23 season, and that's when we'll install the second turbine, giving us duty and standby. And we're also going to deploy a large experiment, an atmospheric radar, which is sort of container sized and takes quite a lot of mast stuff to hold the antennas. And longer term, what we'd like to do is look at reducing the amount of fuel we're running, both to reduce our carbon impact, but also just to make us more resilient as well, so that we don't have to keep going back with so much fuel at Halley. You know, we're having to, although we've got a lot of fuel at Halley at the moment, you know, eventually we'll have to refuel it at 40 tons, 50 tons each year for the turbine. Okay, so it's probably, there's two things we can do now. I can either take questions, or we can just have a look and see what's actually happening at Halley right now. I don't know what's happening at Halley right now. I forgot about this, so I haven't actually checked, but hopefully it's still running.
Yeah, thank you so much for the talk. We do have two questions that have come in so far. Maybe if you want to move to the dashboard while I ask these first ones. The first one came from Jack Dibb, asking why photovoltaics could not be mounted on all these modules, since the modules are self-raising themselves.
Yeah, so we would probably we probably would put quite a lot of the photovoltaics on the modules, but the modules actually aren't very well aligned for photovoltaics, and we would have needed additional ones either side. So the modules are quite well, you know, they're reasonably big, and they would give us quite a good yield in the middle of summer. And in fact, we intend, you know, we're still having to send people to Halley each summer. So, you know, we're this summer season just gone, we had 20 people at Halley, essentially, you know, maintaining the infrastructure of Halley and maintaining the microturbine and raising some science experiments and things like that. And of course, they use vehicles and they use fuel. And we're hoping to reduce the amount of fuel that those people use by putting photovoltaics on the modules, and that does actually works quite well or we anticipate it will work quite well in December and January. But both the angles of the modules and the size of panel area that you've got available isn't enough, and so you need to have panels that would be off the modules, and then they need some way of raising. And of course the batteries also would need somewhere. Again, you know, there is a possibility we could put them on the station. I mean, I think to be brutally honest with you, I think we're still I'll probably get told off if I say this, but never mind. We're probably still going through a process.
Reminded it is recorded, yeah.
Yeah, we haven't given up on Halley being a wintering station yet. So we haven't gone, well, all of these parts of the station which were, you know, designed for people to winter in and for personnel, you know, we haven't reassigned any of them to be anything other than their original design. You know, we haven't gone, well, you know, let's rip out all the bedrooms and make them into batteries, you know, room for batteries. We haven't gone down that route yet. And in fact, because Halley, you know, was relatively new when we started this, we took a decision that in winter, we wouldn't actually, when it was automated, we wouldn't be running any electricity into the main modules of the station, because we didn't want the possibility of burning down the station, you know, unattended, and I certainly didn't want that responsibility. So what we did was all of the science is in satellite buildings, in things like containers on legs and things like that. The actual main modules don't have any power running in them in winter.
Got it. Yeah, and then we have a couple more questions. Two people asked about waste heat. So understanding that power production was a priority, was consideration given to capitalizing on the waste heat from the micro turbine through heat exchange to temper or protect any equipment spaces?
Yes, we did actually. We thought about that for quite a lot, and we are still thinking about it. So in a way, the waste heat, we do use a lot of the waste heat of the turbine is used to warm the air that comes in to run the turbine. The turbine, is a jet engine. It does use quite a lot of air. So, and overall, it's slightly less efficient than a diesel engine. So we do use that waste heat to heat the air by having that pipe within a pipe heat exchanger. But we don't use it anywhere else just because of the geographical constraints of Halley. There was sort of really no way of us doing it. The space science experiments are all in what we call the electromagnetically quiet area. So they're all in a place that we really work quite hard at making sure that they're about 1 kilometre away from the turbine, and they're in an area which is kept very interference free. And then the clean air sector experiments, the air chemistry experiments, are also about 1 kilometre away in a different direction, and they're kept chemically clean. So the exhaust from the generator, for instance, the prevailing wind blows away from the clean air sector, and and we don't take vehicles there more than we have to, and things like that. So the geographical spacing didn't really enable waste heat use more than that. Although it is something that we keep coming back to. So when we have the duty and standby, we would like to use the waste heat of one generator to keep the other one warm. And we do keep having sort of wild ideas, which we just haven't had time to implement. But, just having a reservoir of warm water at Halley would be, or, not ice anyway, would be of a huge benefit for when the team first arrived back at the station each summer season. So if they arrived and there was, a couple of cubic meters of warm water sitting there waiting for them, that actually means that their startup procedures for getting the accommodation going is a lot faster.
Got it. Another question we have is from Monty. So you said that you were averaging about 9 kilowatts of load. Is that fairly steady? Does it fluctuate up and down? Has the turbine had any unexpected shutdowns?
Sorry, what was the last piece of that question?
Has the turbine had any unexpected shutdowns?
No, so not. It had in the season that we got it running, we had one unexpected shutdown whilst we were there. So it shut down as these things always happen in the middle of the night. It shut down in the middle of the night, and we all got alerts and got up and went and started it again. And that, we're pretty certain that was almost certainly, we get quite a lot of fault information recorded from the turbine, and it was almost certainly a loose connector in the battery harness that of the turbine itself. So the turbine actually generates high frequency AC, and that gets rectified down actively. That gets that goes into batteries, and then there's active circuits to produce the mains out from the batteries. So the turbine is always topping up the batteries, and then we use power off the batteries essentially. And it was a loose connector within that within the battery harness, and it caused a communications error, and that was a fatal fault for the turbine, so it turned off. But other than that, we have had no shutdowns at all. So it's been running now for over 2 years with no shutdown, other than when we go in and do the service.
That's great. I think the first part of that question was, because I remember one point in the talk you had saying that it doesn't like low loads. So
yeah. So the actual science equipment that we've currently got on it, it does vary. Some bits vary a bit, you know. So things like the auto Dobson, you know, the servos turn on and off and things like that. But quite a lot of the load is reasonably constant. You know, we have quite a lot of, you know, there's things like the computer servers, automatic monitoring equipment, which is just running all the time and doesn't really change its load. So the biggest component of changing the load is actually heating. We most of the buildings we allow, even though they've got science equipment in them, we allow to run cold and let them go to ambient. Although there's a few that we keep warm at various levels for various reasons. The equipment in there is, you know, is not that good at going cold temperatures. So the space sciences container, we keep that above 5 degrees centigrade. So most of the time it doesn't need any extra heating, only what is waste heat from the experiments. But occasionally, if it's very cold or very windy, the heaters on there come in. And the VSAT, the communication system container, which is where all the computers for the data servers are, or one set of them is, we keep that one at 15 degrees centigrade, just because the VSAT is happier at those temperatures. So, and it's the heaters turning on and off, which gives us the varying loads. And our load bank automatically compensates. So our load bank keeps the average power at about 9 kilowatts. One of the upshots of that, of course, is if we add more science experiments, it means that that doesn't actually cost us any fuel at the moment, because it just means that we would add a bit more load on as science, and that the load bank would need to operate less to keep above a minimum load. So at the moment we've got, you know, we've got power to play with, and we can go up to about 28 kilowatts of power if we need to.
Thanks. I think there's another question asking, what's the percentage of uptime that you've been able to achieve with the microturbine?
Yeah, so it's effectively 100% really. I mean, the on the turbine, you know, it's run all the time when so that is running 100%. And when we you know, we turn the turbine off for about a week to do the servicing and the moving of things around in the container during the summer season. And whilst that was happening, the experiments were being fed from the diesel generator source that was being used to also provide power to the accommodation block. So power-wise, we're so far we've managed 100%. The individual experiments, we've had the odd experiment which has failed for unrelated reasons. We had one experiment and an antenna had broken. Another one, the GPS rollover didn't happen properly, or we had to. Another one, we had a PC problem, and those sort of things. But the actual main infrastructure, we're touch wood at 100%.
Awesome. And the next question is, do you see BAS moving away from traditional diesel engine generators and going more exclusively to the microturbine model, or is this just a case that works really well for this specific station?
Yeah, so again, we have talked about that, but I think we've really more or less decided that for our main stations, you know, for places like Rothera and King Edward Point on our island stations, that that if we were to transition away from diesel generators, that we want to transition to a close to no carbon source, so that we would, you know, for Rothera, for instance, we're doing quite a lot of work at the moment to work out what that future looks like without diesel generators, with wind generators, solar power, and or whatever it actually happens to end up as. So I don't think we'll end up, although we did initially think about whether we would go to microturbines on our station because of the benefit they give you of reliability and not having to service them every few days. But as I say, I don't think we will do that now. We'll just go straight to a no or low carbon source for the stations. One of the points I often like to try and make is actually, you know, for Halley, the big carbon saving has been not having people there. So, you know, that's, you know, we're using 1/10 of the fuel that we would use to get the same amount of science by not having people really. So it's you know, not only choosing what technology is best to provide the power, but it's also actually, you know, really looking at paradigm shifts on power usage. So automating, you know, flying UAVs rather than planes, things like that.
Okay, yeah, and then we have one last question, and then maybe if we could look at the dashboard real fast. So from Scott, I didn't see any venting on the interior fuel tank. Does that create any expansion issues of the fuel tank?
No, so there is venting on the interior fuel tank. Again, there was a little bit of complication around that. Initially, we had that venting to the outside world, and the basis for that was when you do a refill, when you're you know, so during the periodic refills of filling up the day tank, obviously we put in about 250 litres of fuel each time, and 250 litres of air has to go somewhere, and that air is fairly heavily saturated with diesel fumes, and we wanted to ensure that we didn't generate a flammable or explosive atmosphere in the container. So initially we thought about having it venting to the outside world so that we didn't generate an explosive atmosphere in the container. But once we'd done some more calculations on that, we realized that we couldn't actually get the parts per million of diesel in the container up to the necessary amount to make it an issue. So we then vented back inside the container. So that was because it's more reliable. It doesn't have any possibility of blocking snow or anything like that.
Great, thanks. Yeah, I just want to be respectful of everybody's time. We're at the top of the hour, so maybe we'll end with questions. Mike, do you have time to show the dashboard really fast, or?
Yeah, I have. I'll probably just freeze for 15 seconds while I do this, but let's try
no
it.
worries.
I just have to. I should have done this before, but I forgot about it. So,
no, it's okay. I kind of sprung the question. I think a lot of people had
the
questions. So.
VPN.
And I actually have a question while you're bringing that up. What's your guys' biggest operational challenge for the crew returning after you've been after everyone's?
All right, so I think I'm back.
Oh, okay. You are back.
What's our biggest operational challenge?
Yeah, for the crew coming back after the station's been, I guess,
yeah, it's really the biggest challenge is just, you know, is raising everything at Halley, and we're trying to do that with a small crew that we can put in and out by air. And the problem is we've got a station which was designed to hold a wintering team of up to 20 and have a summer population of 80, and we've got all of the infrastructure for them, and we have to maintain that infrastructure because it will bury in the snow if we don't. It's the problem with Halley is it's, you know, it is constant maintenance of everything. You can't leave anything because it will bury. And so we're maintaining all this large amount of infrastructure, and yet we're, you know, using less on for the science. So that is our current operational challenge, is just, you know, maintaining things above the snow surface. So if I share my screen again.
Yep, go ahead.
Oops. So are you seeing some graphs?
We are. Yep.
Okay, so this is a live view, and we can zoom in and out of these graphs if we need to, but it takes a bit of a while. So it just shows you where the power, you know, and these update every 30 seconds. So we get we get a new data point every 30 seconds. So it's where the power is going around the station, the power output of the microturbine compared to the amount of power that's actually being used by the station. Again, the power by phase, because it's a 3-phase system. And we don't have very good phase balancing, as you can see. The turbine doesn't actually mind about phase balancing because it's because the 3 phases are taken off the batteries. It doesn't really mind, which is good because we don't have good phase balancing. Again, some current measurements of where it goes. And this is our load bank, which is operating at the moment. So it shows it switching in and out, and it's switching power in on at the moment on phase A and phase B, up to about 500 watts on each of those 2 phases. So this shows our total load that we're using, the temperature in the system, more stuff about load, more stuff about where the power's going, more about where the power's going, more about where the power's going. The bulk tank sensors, they are actually working at the moment, but we've got a data processing issue, so they are not appearing on this graph, but they are actually working. We measure the field temperature on the lines as it comes in. This is the field temperature. You can see the field temperature changes as we go through a refueling. That's when we've gone through a refueling, and that gives us a proxy for what the field temperature is in the bulk tank, which helps us on doing the temperature compensation. This is the day tank level, so levels dropping, gets down to about 1450 litres, and then a refill happens, and then it just drops again as we use fuel. We measure pressure on either side of the fuel pumps, so that would tell us, for instance, if we were sucking air, if there was a leak in the hose, it would tell us on one side, or if we were having problems with the fuel filters on the other, it would give us that, as well as health information about the pumps themselves. More stuff from the generator. It tells us how fast it's spinning. As you can see, it spins along quite fast. Sits there doing 68,000 RPM. State of health of the batteries, what their temperature is, and then lots of temperatures measured around the system. So we have lots of temperatures measuring around the system. And this is the air conditioning fans. So at the moment we're having to bring cold air into the into the container to help it stay at the right temperature, but only a very low value, 2%. And then the other fan is moving air around the container. That's all to do with air conditioning as well, humidities, and then we've got the environmental temperature and wind for the site. So Halley is currently sitting at -10 with about 10 knot wind. And then we have the webcam pictures, some of them which are really boring because they never change. And we have the external ones of the which are looking at really mostly at the fuel lines and the hose termination points. As you can see, it's quite a nice day at Halley at the moment.
Yeah, it looks gorgeous. -10. Great. Well, thank you so much. We do have a couple more questions, but maybe I'll follow up with you on email if you don't mind us picking your brain a little bit.
Yeah, you're happy. Just if you send me the questions, I'll answer them in slow time.
Okay.
And
yeah, that sounds great.
Likewise, if anybody wants, any really specific details or longer term conversation about any aspect of it, then they can email me as well, m.rose@bas.ac.uk.
Great. Well, thank you so much. I can't tell you how much we appreciate you taking the time and following up on what would have been. We missed you last year, definitely at the conference in person, but really.
Yeah, I will make it to Boulder one year.
I know, it's beautiful. It's very, very beautiful. Well, thanks so much. We'll be distributing the recording of the lecture to everybody. I'm sure there's a number of people who couldn't make it today. So it'll be.
No, thank you very much for your attention, and thank you for the excellent questions.
Thanks, everybody.
Okay, thank you.
Bye.
Bye.
Thanks.